Greetings. In today's class under embedded microcontrollers, we look into interrupts. So what is an interrupt? Whenever an external device needs service of the processor, it makes a request. So that is called as an interrupt. So actually speaking, the processor can service the devices either by two methods. One is called as a polling, another one is called as a interrupt. In the case of a polling, the processors will go on checking the external devices whether it needs to be serviced. In the case of interrupt, the processor will be doing its work, and when the external device or a device needs a service of the processor, it makes a request. So in the case of an interrupt, one should understand the processor is not wasting much of its time. In the case of the polling, the processor will be wasting its time because it's go on checking the pins or the devices whether it needs to be serviced. So looking into the difference of the polling and an interrupt, look into the definition. Interrupt is a hardware or a software mechanism where a device notifies the CPU when it requests attention. And when you look into the CPU utilization, it does useful work and only services when an interrupt occurs. Looking into the response time, when an interrupt occurs, usually it is faster. The CPU responds as soon as the interrupt is triggered. And again, this is an event driven interrupt because the processor will be doing its work, and when an event occurs, the processor will be notified that the device needs a service, so hence the device will go and processor will go and service. Looking into the overhead, it requires an interrupt handling mechanism. You will have an interrupt service routine, and the processor will have a main program. In between the main program and an interrupt occurs, the processor will follow more number of steps, and then it moves into the interrupt service routine. So the overhead is little larger and the power consumption is lower. The CPU can go into idle until interrupt occurs. So if it needs another service, it can do, or otherwise it can go into an idle state. So devices, when it is best used is when the events are unpredictable. So if you have a main work for the processor, and the devices can make a request at its own pace. So when you have an unpredictable events occurring, so the interrupts can be working well. And the examples are keyboard, and keyboard, it generates an interrupt that CPU handles immediately. Looking into the polling, the CPU repeatedly checks polls each device or flag in a loop to see if it needs a service. And it's inefficient because the CPU wastes cycles checking devices even when they don't need service. The response time by the processor is slow because it has to complete its immediate work, then it has to go for the polling. And again, it's again a program driven, because by program you should write in an instruction such a way that the processor goes and check time to time whether the devices needs a service. Coming to the overhead feature, requires no special hardware beyond status register but consumes CPU time. Again, the processor is going on checking, so it's wasting its time. The power consumption is high because it has to stay active every time, and this is best used when you have predictable intervals, because time to time the processor can go and check. So from predictable intervals, this can work well. And example, CPU repeatedly checks flags to see if a UART, in case of serial communication, whether a character has been received. And what happens when an interrupt occurs? The processor will be completing its current execution of the instruction, and the return instruction, that is address of the next instruction, will be stored inside the stack. Now what the program counter will be done is, the program counter will be loaded up with the interrupt service routine's address, and then it will jump into the interrupt service routine. This interrupt service routine's program will be continued, and while executing the return from interrupt instruction, all the necessary data and the return address will be restored back from the program counter, and it jumps into the main program. So these are the steps that has to be followed when an interrupt occurs. This is an example of it's a table which denotes interrupt vector table for the PIC 18. You can say the power on reset, it's in the location 0000, and whereas in the case of a higher priority interrupt 0008, lower priority interrupt is 0018. So some of the sources of interrupts in case of PIC 18 is timer interrupt. For example, if you consider you have 3 timers, timer 0, timer 1 and timer 2. Whenever the timer gets overflow, you will have an interrupt that is occurring. And you have additionally 3 external interrupts, namely RB0 which occurs at INT 0, RB1 at INT 1 and RB2 INT 2. That is, interrupt 0 will occur at the pin RB0, interrupt 1 will occur at RB1 and interrupt 2 will occur at RB2 pin, that is a port B pins. USART interrupts, you have 2 interrupts, one for the reception and one for the transmission. That is, when you receive some data, once the reception is over, a reception interrupt flag will be set. And again, when you transmit some data serially, after the transmission is over, transmit interrupt flag will be set. And we have another specific pins for port B, and they are called as a port B change interrupt. So whenever the pin status changes, that may cause an interrupt. And other than this, you have some interrupts for ADC. So once the conversion is over, the ADC interrupt will be set. And you have CCP interrupts, that is capture, compare and pulse width modulation. So when all the events capturing, comparing and pulse width modulation events is over, these interrupts will be caused. And this is an example that has been shown here. You can see here some interrupts like timer 1 interrupt, timer 2 interrupts, transmission, reception, all these are connected into an OR gate. And when the peripheral interrupt enable bit is set, these interrupt will be considered. So when both inputs are 1, it will go into another OR gate. And again, to the first cadre of the OR gate, you can say timer 0 interrupt flag, interrupt 0 external interrupt 1, 0 and 2. All these will be enabled only if the global interrupt enable is set. So any kind of interrupt can work only if global interrupt enable is set. Only if the global interrupt enable is set, any interrupts will be serviced. And again, peripheral interrupt enable has to be set for timer 1, timer 2 and serial communication interrupts. So the vector location will be of a higher priority or a low priority based on the locations, based on the high priority of the interrupts. So how do you enable the interrupts? Enabling the interrupts can happen through the global interrupt enable bit, which is available in the INTCON register. So that has to be set. So only if that is set, that all these interrupts that's connected will be served. And similarly, if GIA is 0, no interrupt can be responded. And some peripheral interrupts like timer 2, timer 1 and transmission and reception interrupt, the PEIE flag must be enabled in addition to that of the global interrupt enable bit. So global interrupt enable bit has to be set once the interrupt has to be serviced. So this is an example that has been shown. This is a register format of the INTCON register. You can see the D7th bit is GIE, and similarly you can see timer 0 interrupt enable flag and interrupt 0 interrupt enable bit. All these are available in the INTCON register. Thank you.